Okay, we're going to cover the last section and then we'll probably have one more video that talks about synthesis and review. So in this reaction, we're going to use the enolate and we're going to use an electrophile that we haven't seen before. So the electrophiles that we have used so far have been the halogens. We've done alpha halogenation. Other electrophiles include ketones. We've done aldehydes. I'll do aldehydes, ketones. We've done esters. The first two are the aldol reactions. The second is the Claisen and Dykman reaction. We've also done the alkyl halides, which includes the malonic ester and the cetoacetic ester synthesis. And so all these electrophiles have these partial positives that the enolate attacks. So the new electrophile is actually going to be this alpha beta unsaturated carbonyl. And I asked you previously, at the end of the last lecture, if you remembered how to make that. Hopefully you put in some mental effort and figured out that that is simply the product of an aldol condensation. If I take OH minus and some heat, then the product that I get out of this, remember we can have the trick where we dock the carbonyl at the alpha position, and ultimately what we end up with is this alpha beta unsaturated carbonyl. Now what's interesting about this alpha beta unsaturated carbonyl is it actually has two electrophilic sites. It has, of course, the electrophilic site at the carbon of the carbonyl, but it also has this electrophilic site out here at the beta carbon. And so let's try to figure out why. So if we look at this first box right here, we pull the electrons up, we can actually see why that carbon of the carbonyl is electron deficient and is an electrophile. If we continue with our resonance structures, that double bond comes over and we can see that we develop a positive charge in this resonance structure. Of course, the resonance structure that best identifies a molecule is the first one. But again, resonance structures tell us something about the reactivity. And so therefore, we actually have two deficient sites. And so we could actually add our nucleophile in two different ways. We could add in what we call a direct addition, which is what we did when we attacked carbonyls, as well as carboxylic acids. So that direct addition is essentially what we did in the aldehyde and ketone chapter. Or what we could do, what's referred to as a conjugate addition, a 1,4 addition. And that's what we're going to focus on in this chapter. We're going to do a conjugate addition. And the nucleophile that we're going to use is going to be an enolate. So let's look at the mechanism of this conjugate addition. This is also known as a Michael addition. So again, another named reaction that you should know. So Michael additions are these additions to the beta carbonyls of an alpha beta unsaturated carbonyl. And they proceed by the nucleophile attacking the beta position. And then that double bond flops over and kicks the electrons up onto the oxygen. Now, if you notice, the product that we get is actually an enolate. And so upon workup, we actually protonate that enolate, converting it into an enol. And hopefully you can guess right now when I say enol, the enols rapidly tautomerize back to their keto form. And so what ends up happening is we get a substitution at the beta carbon. So if we look at this, that's kind of an interesting product. If we just said synthesize that, probably have a hard time trying to figure out how to make it so that there's an electrophile at that site. But these beta substitutions come from these Michael reactions there. In fact, I'll give you a little mental quiz to think about. We showed earlier in the chapter how to do alpha substitution with a nucleophile. So how to substitute a nucleophile here. There's a method that we learned. So see if you can remember that. So we're going to now talk about this beta substitution. We're going to add a nucleophile to that beta. And since we're in the enolate chapter, why don't we use the enolate as the nucleophile, which we will after we talk about the Grignard and the Gilman. So these are essentially two C- reagents. These are carbanion type reagents, is how we look at them. The mechanism's actually a lot more complex, but for our understanding, we can just view them as the carbon attached to these metals, either magnesium or copper, are more electronegative, so they pull electrons away from those metals, excuse me, and they become the nucleophile. Now, Grignard reagents, if you remember, to esters, they added twice, and to acid chlorides, they added twice, and to anhydrides, they added twice. They're what we call strong nucleophiles, very hard, very concentrated negatives. And in the case of these alpha beta unsaturated compounds, again, we have two sites. We have the carbonyl carbon and we have the beta carbon. Grignard reagents add to the carbonyl carbon, as you can see, just like we've always done. Grignard reagents, we always shove up the backside of a carbonyl. Now the Gilman reagent, if you remember, we saw it before with acid chlorides. We took the acid chloride, we took the reagent. Now normally a Grignard would add twice, but the Gilman, being nice, only added once to that acid chloride. And again, we see kind of this different reactivity with the Gilman reagent where it actually attacks at the beta, or does a conjugate addition or a 1,4 addition. And so it substitutes at the beta. So the take-home message is Grignards are always going to add to the carbonyl. Gilman are going to do something different. The acid chlorides and hydrides, they add once. And to alpha beta unsaturated carbonyls, they add to the beta position. So let's talk a little bit more about our favorite nucleophile in this chapter, and that is enolates. So enolates are, again, more like the Gilman reagent, kind of soft nucleophiles that negatives spread over a carbon and an oxygen, and so they tend to add at the beta carbon. So these reactions can actually get a little bit messy when you look at it because you're dealing with a lot of atoms. So one of the biggest problems that people have with these reactions is they tend to lose their atoms. So remember to count your carbons, number them one by one. And it will surprise you that organic chemistry is fun. So what we're going to do is, what we've always done, generate an enolate. Notice this is a doubly resonance stabilized enolate, and so I can actually use a weaker base. So we're just using sodium hydroxide here. It's not an ester, so I don't have to worry about hydrolysis of the esters. We're just going to deprotonate at that alpha position and generate an enolate. Now this enolate here will now come and attack that carbon, kick those electrons over and up onto the oxygen. So where did all those atoms go? So I'll color them. Our enolate is in green, and what they did was just flip it upside down here. Our Michael acceptor, or our alpha beta unsaturated carbonyl, those are synonyms, is in orange right here. And then to finish up the mechanism, once we have this enolate, we just collapse those electrons down and go out to some proton source so that we can end up with a neutral compound right there. So the key to this is that we're adding our enolates to the beta position. And again, you start looking, and now we've got lots of complexity in our molecules. We've got 3 different functional groups there. Notice the arrangement of these carbonyls here. We end up with a 1, 2, 3, 4, 5, a 1,5 dicarbonyl compound. If you ever see a 1,5 dicarbonyl compound, hint is it came from a Michael reaction. A 1,3 dicarbonyl compound came from a Claisen reaction. A 1,3 dioxo, meaning a 1 carbonyl 3 hydroxy group, that came from a aldol reaction. So look for these patterns here. Now we can generate an enolate. In this case here, we're actually using malonic acid. And so, sorry. Okay, sorry about that. Wrong number. So we're talking about adding enolates. In this bottom example here, they're actually using the malonic ester. Notice when they have an ester here, the base that they use, we wouldn't want to use sodium hydroxide here. If we use sodium hydroxide like we did in that upper example, we would actually hydrolyze that ester. So just something to watch out for. We don't have to worry about it in this top example because there is no ester there. Oh, I think I'm having technical difficulties since I paused it. So give me just one more second and I will be back. Okay, I think I sorted it out. So we're back to talking about enolates, adding to alpha beta unsaturated carbonyls. I believe I was talking about the base that you use. Notice here, they're using sodium hydroxide. That's not an issue with this molecule because the only acidic protons and site of reactivity is that alpha position. If we happen to use sodium hydroxide with diethyl malonate, you would actually get hydrolysis of the esters. So that's just something that you want to watch for and make sure. But in the end, the key is that we've added our enolate group to the beta position of these alpha beta unsaturated carbonyls. So what you want to do is look at the reagents. I've got a enolate, and this reaction is really good when you have a particularly stable enolate ion, meaning that the Michael reaction works out best when you have a dicarbonyl, so you can get the double resonance. The base will deprotonate that alpha position. That alpha position will attack, kick those electrons over and up. That gives you the intermediate product. That is the enolate. O minus. And we have the double bond there. And then what happens is when you work this up, just a gentle amount of acid. Oh, sorry, I missed a carbon there. Then this would come out and get protonated. So notice the bond in red right there. That is the bond that you make. Here's the alpha carbon that attacked. Here's the beta carbon. I'll actually put that in red. That's the beta carbonyl, or beta carbon that you attacked. And here's the bond that you formed. So again, we're going to connect the alpha carbon from this doubly resonant stabilized enolate to the beta carbon of an alpha beta unsaturated carbonyl. And as it shows, that bond is what's made by the Michael reaction. So we just simply connect here, get rid of the double bond. So we're going to have a bond there and get rid of the double bond. And so we end up with molecules that look like this, these 1, 2, 3, 4, 5 dicarbonyls, so 1,5-dicarbonyls. And so I just got a little question here for you. Look at this final product. And does it look familiar? Have you ever seen anything like that final product? Anything that looks like this before? Okay, we'll come back to that. So the Michael reaction, again, excuse me, what we're doing is we're adding that alpha carbon from the enolate to the beta carbon of a alpha beta unsaturated carbonyl. So what do we want for Michael donors? So good Michael donors are those that tend to be doubly resonance stabilized, those that have 2 carbonyls, or like in this case here, you actually have somewhere for those electrons to move. So we've got 2 directions for the electrons to move into. I'll draw out the NO2 group so you can actually see how that can be involved in resonance. So you can move those electrons over and up onto that oxygen there, as well as the Gilman reagent. And then good Michael acceptors, what do we need for those? Well, really, we just need these alpha beta unsaturated carbonyls. Those are what we need. We can have other electron donating groups like amides or esters, and those still work as Michael acceptors. And you can also have groups like nitriles that pull away electrons, or nitro groups that also have the option to pull away electrons there. But the key is you want this double bond in conjugation with a C double bond O, or in this case down here, a C triple bond N, or an N double bond O right there. So that's the generality of the Michael reaction. So as you see here to the left, this is a good Michael donor because it's doubly resonance stabilized, and this is not a good Michael donor. So even though we can form enolates from this species here, it's not a very good Michael donor. And so you're just, the reaction will still work, but just as it notes here, not obtained in good yields. So like I said, the reaction will still work. So what do we do if we only have 1 carbonyl on there? How can we still do a Michael reaction? And of course, the answer is yes. So someone came up to a solution to that problem. And by name of Gilbert Stork at Columbia University, came up with a way to actually use compounds that only have 1 carbonyl. And this is called the Gilbert-Stork enamine synthesis. So back in the aldehyde ketone chapter, we talked about the reaction between amines, and especially secondary amines and carbonyls. So you can't forget anything. So in this case here, you should remember that secondary amines, when they react with ketones, give you this ene amine structure. So that's where the name enamine comes from, because it's an amine that is connected to a double bond. So enamines. So if we make an enamine, if you squint really hard, that looks an awful lot like a enolate, other than you don't have the negative charge. So enolates, those electrons can drop down and kick out and come and grab an electrophile. Lo and behold, we have a lone pair on that nitrogen, and it can actually react in the same way. So if you happen to have just a single carbonyl and you want to do a Michael reaction, you can do it. But like we saw up here, you can't just use LDA to form the enolate. The solution is you form an enamine. that is like an enolate surrogate. So as you can see here, as I just showed you on the previous slide, enolate ions are very similar in their electronic character to enamines. And so just like a enolate can drop down and attack an electrophile, which is what we've been doing this entire chapter, enamines can also drop down and attack electrophiles. And this is a solution to the problem of doing Michael additions, where we only have one carbonyl. So this type of reaction here, if we were going to do it with a alpha beta unsaturated carbonyl, it would be a poor yield. But if we did this reaction here with the Gilbert-Stork enamine, we would get a good yield. So this Gilbert-Stork enamine reaction actually solves a problem. And so we can actually do alkylations and the other enolate reactions. And in fact, there's some benefits to it. These enamines are actually shelf stable. So you can synthesize them and then just have them sitting on your shelf, and you can pull them out when you need them. You don't necessarily need to generate the enolate. You just pull the enamine off the shelf. So if you don't remember this mechanism, look back to the carbonyl chapter or that handout that I gave you. So when you add a secondary amine with just a little bit of acid, you get an enamine. And then that enamine can react with electrophiles like it does in this case. It does the alkylation, and then we end up with this iminium ion. And back to the carbonyl chapter, or the aldehyde ketone chapter, when we have imines and we add acid and water, that water will eventually drive in there and kick off that secondary amine, and we get back the carbonyl. So as I mentioned, some of the advantages are the enamines are shelf stable, as well as we're not in strongly basic or acidic conditions for this. We're in fairly neutral conditions. So this is actually a very efficient way to do a lot of these reactions. So like I said, you can do the alkylation, but really the problem that it solves is this reaction with the Michael reaction. So again, this cyclohexanone is, we wouldn't consider it to be a good Michael donor, but when we make it into an enamine, it is now a good Michael donor. And so what we can do is the Michael reaction. And that mechanism is shown down here. Just like in an enolate, those electrons would drop down, come out from the alpha position. We kick the double bond over and the electrons up onto the oxygen. We end up with this enolate intermediate that those electrons collapse down. And just like in any old Michael reaction, we would protonate to get back our carbonyl. And we've got this iminium ion. We want to get rid of it and unmask the carbonyl. And so just a little bit of water to come in. Oh, attacking the wrong spot. There we go. Let's attack the iminium ion, kick the electrons up, do some proton shuffling. We can actually get back to our carbonyl. And so notice at the alpha position here, we've formed a new bond, and that is to the beta carbon. And we've actually done a Michael reaction with what looks like a poor Michael donor. So a great reaction for the alkylation at the alpha carbon is the Stork reaction. And here's just some more examples of what we're doing. So cyclohexanone, the mechanism. And again, we get this guy right here. And remember, from a Michael reaction, we always get a 1,5-dicarbonyl. And if we redraw that, that's kind of interesting. Just a few moments ago, I said, you know, that's an interesting looking molecule, and here we see it again. Is there anything that we could do with this molecule? Have we seen that before in any of the reactions? Still waiting. I'm waiting for an answer. I'll sit here until someone answers. and I may be sitting for a long time. You're probably yelling at your screen that that's an intramolecular aldol, and you're correct. We can do an intramolecular aldol reaction with that. So what's really cool about these Michael reactions is we get these 1,5-dicarbonyls that can go on and do further reactions. So if you ever see a synthesis that wants you to make a 1,5-dicarbonyl, the key is find one of those carbonyls there and pick the alpha carbon. And from that alpha carbon, you're going to disconnect. And when I disconnect there, then that would make the double bond here. And some of you are saying, well, why couldn't I disconnect here, use my alpha carbon there, and make my double bond right there? You probably could. You can kind of tell which way they want you to go is to disconnect here, because there's no alpha carbon here. There's an alpha carbon here. And so that way I can control. And so I'm going to put my double bond right there. Now, if we break that apart, this is the enolate that I need. But again, that is only a singly resonance stabilized enolate. So it's not going to be a very good Michael donor. I'm not going to have much success in this reaction. I will get some product, just not a lot. So what I want to do is, instead of actually use this enolate, what I want to do is use an equivalent. In organic chemistry, we actually refer to this as a synthon, a synthetic equivalent to an enolate. And so enamines are synthetic equivalents to enolates. And how we form them is just with the secondary amine and a little bit of acid. We lose water as our leaving group. And then the reaction, those electrons come down and we come in and attack there. And again, there's the alpha carbon, there's the beta carbon that we attack, and we have a 1, 2, 3, 4, 5 dicarbonyl compound. Okay, so here's an interesting reaction. We're going to deprotonate here and attack at the beta position there and get this 1, 2, 3, 4, 5, 1, 5 dicarbonyl compound. But notice I actually get this alpha carbon right here. And if I count from this alpha carbon, 1, 2, 3, 4, 5, 6, that's 6 carbons away. So would it be possible to form an enolate that then attacks that carbonyl there to do an intramolecular aldol? And if I added heat, what I should be able to do is essentially just make a double bond there. And so we could see that NaOH and heat, we do an intramolecular aldol condensation with a double bond. And now what we've done is we've fused the rings there. Now this is a two-step reaction. It's a Michael reaction followed by a aldol reaction. And instead of calling it a Michael reaction followed by an intramolecular aldol reaction, we give it the name of the person that discovered it, which is the Robinson annulation reaction. Annulation comes from annulus, or ring formation. And again, all Robinson did was combine a Michael reaction with an intramolecular aldol reaction and got his name on a reaction. So if you're out there looking at reactions, say, gosh, I'm going to put two reactions together and call it the Stephenson reaction. So the key to the Michael reaction is we have to do this, the key to the Robinson annulation is we have to do the Michael followed by the intramolecular aldol. And I told you that this is a poor Michael donor, but just for the sake of this example, we're going to use it as our enolate. The better way to do this would be the Gilbert-Stork, but with a base, we can deprotonate there. And again, what I'm just trying to show is that I get this 1, 2, 3, 4, 5, 6. So a connection from one alpha carbon to that carbonyl is 6. It's a 1, 2, 3, 4, 5, a 1,5 dicarbonyl, which you always get from a Michael reaction. But in this case, when I get this Michael reaction, I actually have some alpha protons out here that if I use as my nucleophile can close up there and give me a 6-membered ring. Remember when we did the intramolecular aldol, we counted from the alpha position. So I could start here, count 1, 2, 3, 4. Well, I don't want a 4-membered ring. A 1, 2, 3, 4, 5, 6-membered ring would be much better. And so if we add an OH minus, what we do is we form an enolate, kick those electrons up, we get the aldol product, and then we follow that up by the aldol condensation with some heat, and we get this cyclohexenone. And that is the product of a Robinson annulation. This is a cyclohexenone. So here is the complete mechanism. We're going to deprotonate. Again, this is out of a different book, and they're not using a really good Michael donor. Like I said, it still can happen. What we'd love is that we have another dicarbonyl there. That makes a much better Michael donor. But again, for this example, just to show where the atoms are going, this will work. Maybe our yield would be low, but we deprotonate at that alpha position and we get an enolate. Again, we would prefer to have a doubly resonance stabilized enolate, but we'll take what we've got and attack the beta position here, kicking the electrons over so they end up on the oxygen there. We then have an enolate that gets protonated and regenerates our carbonyl, our ketone here. We have this alpha carbon here that can then be deprotonated by the base that's in solution. So this is an all-in-one-pot reaction. You just add some base and some heat and just let this reaction go. That deprotonates, attacks that carbonyl. We end up with an O- that gets protonated, and we have the aldol addition. And then what happens is we deprotonate. Remember, I don't do an E2 reaction. It would be improper to pull that electron off, collapse those down, and kick out the OH. We pull off that H, park those electrons on the alpha position, and draw that structure, and then collapse those in and kick out that O-. In fact, if you wanted to, pull off that H, put the electrons here and up onto that oxygen there. So I'll draw that structure here. So then what we have is an O-, and then that minus collapses down. Those electrons pop over, and that's what kicks off the OH-. And again, OH- isn't a good leaving group, but we do get a conjugated system through a double bond and a double bonded oxygen there. So that's one of the driving forces for the intramolecular aldol, is that conjugation, even though we have a poor leaving group. So this whole thing right here, these 3 steps, the Michael addition followed by an intramolecular aldol addition followed by a aldol condensation, or we can just what you can say for the Robinson annulation is a Michael addition followed by an intramolecular aldol condensation, is how we get these cyclohexanones, again, known as the Robinson annulation. So they give us these interesting molecules, again, starting with the Michael product and then the annulation product. And we can go from simple molecules to very complex. So in this bottom box here, you can actually see that they use this reaction. So in this case, they've got a acidic proton. This is going to be a good Michael donor because we've got double resonance stabilization. And we'll attack that beta position to actually get this Michael product right there. And then we're going to use this alpha proton to attack that carbonyl and get a double bond right here. And then they do some more magic. That's what these double arrows mean, to connect from here to here, and a few other modifications. And you can actually make hormones. So from fairly simple precursors, this Robinson annulation allows making fairly complex molecules. And so in the early synthesis of steroids and other polycyclic molecules, this was a very useful reaction, the Robinson annulation. And we've reached the end. So in the final lecture of this chapter, I'll talk about synthesis strategies. We'll review the reactions. Right now, just briefly, what that will entail is talking about this arrangement of functional groups. So beta hydroxycarbonyls come from aldol reactions. Alpha beta unsaturated carbonyls come from aldol condensations. Beta ketoesters come from Claisen reactions. This 1,5-dicarbonyl actually comes from Michael reactions, which we can also do by the storquinamine. So in the next lecture, we'll actually talk more about that and how you can use these reactions to make some really complex and interesting molecules. We'll talk to you then.